Many industrial hydraulic systems include accumulators and cylinders. An accumulator is used to store hydraulic energy, while cylinders are used to convert hydraulic energy into mechanical motion to do work. In this lesson, we'll take a close look at both accumulators and cylinders to see how they operate and how each is used in hydraulic systems. Let's start with accumulators. Hydraulic accumulators store hydraulic fluid under pressure. The accumulator is filled or charged with pressurized fluid that is stored as potential energy. This energy can perform work when the accumulator is emptied or discharged. In hydraulic systems, this energy is used to develop flow, to maintain pressure, and to reduce the effects of hydraulic shock. Accumulators used to develop flow can increase flow when the demands of the system are greater than the pump can deliver. Suppose, for example, that a machine operates only once every 10 minutes, but requires 10 gallons delivered in 1 minute. A 10-gallon per minute pump could be used, but it would idle for 9 out of 10 minutes, work for a minute, then idle for another 9 minutes, and so on. The pump and its motor would waste power idling. The same work could also be done with a less expensive 1 gallon per minute pump and motor and with an accumulator that has a working volume of 9 gallons. For 9 minutes, the pump would store energy as pressurized fluid in the accumulator, then supplement flow from the accumulator during the 10th minute. Accumulators are also used to maintain pressure in hydraulic systems by compensating for both increases and decreases in pressure. For example, the fluid in a hydraulic system operating in a hot environment will expand and could increase pressure enough to damage components, fittings, or piping. However, a properly sized accumulator installed in the system will take up the extra fluid volume created when heat expands the fluid. As a result, pressure will remain relatively constant. Accumulators can also maintain pressure in one part of a system as pump flow is diverted for use elsewhere. For example, these two cylinders will extend at the same time to clamp a part securely in place. But if the upper valve is shifted to retract the upper cylinder, pressure drops. The check valve isolates this part of the system from the pressure drop, and the accumulator stores sufficient fluid under pressure to make up for pressure losses caused by normal leakage. Accumulators are also used to absorb hydraulic shock. Hydraulic shock can be caused when system flow suddenly changes direction, as when a directional control valve is shifted quickly. Shock may also occur when a valve is quickly closed, suddenly stopping the flow of hydraulic fluid to part of the system. Hydraulic shock can cause fittings to leak and components to fail. An accumulator in the circuit can absorb some of this shock, reducing the effect on other areas or components in the system. 3 types of accumulators are used: weight-loaded, spring-loaded, and hydro-pneumatic. Weight-loaded accumulators apply a force by means of weights. The weight can be of any heavy material such as concrete, metal, even water. Weight-loaded accumulators are usually large, and they often service several hydraulic systems at once. This type of accumulator provides constant pressure because the weight does not change as the accumulated fluid is discharged. However, the inertia of the weight can create shock when discharge from the accumulator is suddenly stopped. A spring-loaded accumulator has a spring that is compressed as fluid is pumped into the accumulator. The fluid pressure increases as the spring is compressed. When the accumulator is discharged, the spring decompresses and fluid pressure decreases. The spring chamber on a spring-loaded accumulator is vented to prevent the buildup of fluid which may leak past the piston. Excessive foaming and leakage at the vent are usually good indications that the accumulator requires repair or replacement. One of the most common accumulators is the hydro-pneumatic type. They operate essentially the same as spring-loaded units, except they use a compressed gas in place of a mechanical spring to store energy. There are several kinds of hydro-pneumatic accumulators. One kind has a moving piston which separates the gas from the hydraulic fluid. A second kind uses a flexible diaphragm. And the third kind uses a rubber bag or bladder inside a steel shell or housing. Let's take a closer look at how hydro-pneumatic accumulators work. Before this type of accumulator is used, it must be pre-charged or filled up with compressed gas. If the proper pre-charge is not applied and maintained, the accumulator will not operate correctly. Only dry nitrogen should be used as a charging gas. Never used compressed air, because it may create an explosive vapor of air and oil. After the accumulator has been pre-charged with nitrogen, it is ready to be used. To develop flow or to maintain fluid pressure, the accumulator must be filled with fluid until the nitrogen pre-charge reaches a specific maximum pressure. Then, as the system requires flow or pressure, the accumulator discharges fluid until the pressure of the pre-charged nitrogen drops to a specific minimum level. The volume of fluid the accumulator discharges between a maximum pressure and a minimum pressure is called the accumulator's usable volume. The usable volume in an accumulator depends on how quickly the accumulator is filled with fluid, how rapidly it is discharged, and on the pressure of the pre-charged gas. When an accumulator is filled with fluid quickly, the gas pre-charge heats up as it compresses, and so it occupies more space in the accumulator than if it had remained cool. The more space the gas pre-charge takes up, the less usable volume there is for the fluid to occupy. This is called adiabatic charging. However, if the accumulator is filled with fluid slowly enough that the gas pre-charge heats up very little, the usable volume will be larger because the gas takes up less space. This is called isothermal charging. Discharging fluid from an accumulator can also be done adiabatically or isothermally, and the effect on usable volume is very similar. When fluid is discharged rapidly, less fluid is released because the pre-charge doesn't have time to expand as much as it would have if the accumulator had been discharged more slowly. The other factor that affects accumulator performance is the pressure of the pre-charge. Charts are available which roughly indicate the change in usable volume as a result of changes in pre-charge pressure. However, equations are usually used to determine the appropriate pre-charge. Over time, pre-charge pressures in hydro-pneumatic accumulators tend to gradually dissipate. Therefore, maintenance schedules for systems using hydro-pneumatic accumulators should include routine checks of pre-charge pressures. For example, the pre-charge on this accumulator has dropped to 700 psi, down from the specified pre-charge of 900 psi. Always pre-charge an accumulator to the recommended pressure, because pre-charging at too high or too low a pressure could greatly change system performance. Often, when an accumulator is fully charged but no work is required of the system for a period of time, the pump is dumped to tank at a low pressure until the accumulator requires recharging. This is called unloading, and it conserves energy and reduces wear on the pump and its motor. One common way of unloading is with a differential unloading relief valve. This valve, specifically designed for use with accumulators, will automatically divert flow to the accumulator whenever it requires charging, but will unload the pump to tank after the accumulator is charged. In this system, for example, the valve opens and unloads to tank when the accumulator is fully charged at 1000 psi. As the energy in the accumulator is used up, pressure upstream of the check valve drops. When pressure drops to 850 psi, the valve closes and flow from the pump fills the accumulator again. This special relief valve includes a main valve spool, a check valve, a pilot line, a spring-biased pilot valve dart, and a differential piston. They work together to enable the valve to open and close as pressure rises and falls. Here's how it works. When the accumulator is being filled, flow from the pump, shown in red, goes past the check valve and into the accumulator, filling it with fluid. Fluid at the same pressure also goes through a pilot passage to one end of the differential piston, and through another passage to the other end of the piston and to the face of the dart. In this case, the spring tension on the dart has been adjusted so the dart remains seated until pressure rises to 1,000 psi. When that happens, the dart unseats slightly, allowing some fluid to flow past the dart and return to tank. This flow to tank is shown as blue. The flow past the dart reduces pressure on one side of the differential piston. This reduced pressure is shown as orange. Since there is less pressure on one side of the piston, it shifts in that direction, forcing the dart completely off its seat. With the dart forced off its seat, pressure on the spring side of the main valve spool drops. This pressure is shown in orange in this illustration. The main valve spool shifts, opening a passage from the pump directly to tank. When that happens, inlet pressure drops, and the check valve closes, preventing the accumulator from discharging through the relief valve to tank. However, when the accumulator discharges enough fluid into the system that its pressure drops to 850 psi, the pressure on one side of the differential piston also drops. When this happens, the piston shifts back. The tension of the spring reseats the dart, and pressure begins rising again as the accumulator fills with fluid. The pressure differential at which the valve operates depends upon the difference between the area of the face of the piston and the area of the dart tip. Typically, the piston face is 15% larger than the dart tip. Therefore, the piston doesn't shift back until pressure on the accumulator side has dropped to 15% less than what it took to open the dart in the first place. In this way, a differential unloading relief valve allows the pump and motor to unload when an accumulator is filled, and to remain unloaded until the accumulator needs to be filled again. One last important thing about accumulators. Since accumulators store energy in the form of pressurized liquid, there should always be some method of automatically releasing this stored energy when the system is shut down. This reduces the possibility of unexpected movement of system components during maintenance operations. Okay, now let's take a look at hydraulic cylinders. You'll remember from earlier lessons that cylinders are used to convert the energy of pressurized fluid into mechanical energy. In a cylinder, the pressure differential between the cap end and the rod or head end of the cylinder can be very high, so the piston must be sealed at the cylinder body to prevent leakage as the piston moves the rod in and out. This is done with cast iron piston rings or with seals made of a flexible material. Cast iron rings last longer but may allow unwanted leakage. Flexible seals may not last as long as cast iron but do form a positive seal. The seal on the rod, the gland seal, has two purposes: to prevent fluid from escaping and to prevent dirt from being carried into the cylinder as the rod retracts. A primary seal allows the rod to move through the cylinder body without allowing fluid to escape. A wiper seal cleans the rod, keeping dirt out of the cylinder. The space between the seals may be externally drained to prevent the accumulation of excess fluid. Now, all seals can eventually wear out. Worn-out rod seals are often easy to spot because of the leaking fluid on or near the rod end of the cylinder. But leaks past worn piston rings or seals inside a cylinder aren't so easy to find. Most piston rings are designed to allow some leakage for lubrication purposes, but problems will begin to develop if a piston bypasses too much fluid. Since excessive leaking past piston rings reduces flow, one indication of leaky rings is reduced speed. You can identify pistons that are bypassing fluid by carefully measuring their speed at a particular pressure and comparing it to the speed at which they should be operating. Another potential problem with cylinders is hydraulic shock. Sometimes this shock can be severe enough to damage the cylinder. Many cylinders include a cushion to slow down the piston as it approaches the end of its stroke. This reduces the shock and helps prevent damage to the cylinder and the system. The cushion may consist of a needle valve in the end of the cylinder and a plug or spear attached to the piston. As the piston nears the end of its stroke, the spear blocks the opening, forcing the fluid left in this area out past the needle valve. Adjustments of the needle valve determine the extent of the cushioning action. Sometimes stop tubes are installed in cylinders to help provide support for long piston rods. The tube helps minimize damage to the rod gland and to the inside of the cylinder body. Now, there are several different kinds of cylinders used in industrial hydraulics, depending upon the specific application. One common type is the single-rod, single-acting cylinder, which has fluid pressure applied to only one side of the piston. The return stroke is accomplished by some external means, such as gravity or a spring. A double-acting cylinder is one in which fluid pressure can be applied to either side of the piston. Tandem cylinders have two or more pistons connected to the same rod. This allows system pressure to be applied to each piston, increasing the force the cylinder produces without having to use a cylinder with a large diameter piston. Unlike tandem cylinders, where the pistons are joined to the same rod, the rods in a duplex cylinder are not connected. Each rod has a different stroke. This allows the load to be moved to several positions. For example, this duplex cylinder, with strokes of 6 inches and 10 inches, can move loads to one position when both pistons are at one end, to another position when the 6-inch stroke is extended, and to a third position when the 10-inch stroke is extended. In some applications, a cylinder must extend and retract its rod at the same velocity. When this is necessary, a double rod cylinder can be used. As long as the rods on both sides of a piston are the same diameter, the area on each side of the piston exposed to flow will also be equal, so rod velocity will be the same. Another way to match the velocity of rod extension and retraction is to use a 2-to-1 cylinder in a regenerative circuit. In a 2-to-1 cylinder, the area of the piston at the cap end is twice the area at the rod end. If flow on extension were equal to flow on retraction, then the rod would extend slower than it retracted because there is more volume to be filled on the cap side. However, when used in a regenerative circuit, fluid from the rod end is discharged back into the cap end, increasing the total flow and equalizing the speed. One disadvantage of regeneration is that when the rod reaches the workpiece, there is less force available to move the load. This is because the same pressure is being applied to both sides of the piston as the rod extends, and the pressure creates a force in both directions. Part of the force being applied to the cap side of the piston has to be used to overcome the opposing force from the rod side, leaving less force that can be applied to the workpiece. Once the rod reaches the workpiece, the opposing force on the rod side can be eliminated by allowing the fluid to dump to tank through a special type of directional control valve. Without the opposing force from the rod end, the total force developed on the cap side of the piston is applied to the workpiece. This completes our lesson on accumulators and cylinders. In the next lesson, we'll take a detailed look at flow control valves.